I'm Sam, and I'm going to present our paper, Ghostor, Toward a Secure Data Sharing System from Decentralized Trust. This is joint work with Yuncong and Raluca Popa, also with UC Berkeley. I'm going to begin with a motivating example in order to put our work in context. So suppose you have a storage server, and suppose two users, say Alice and her doctor, are both using the storage server, and they're reading and writing the same files in order to communicate or share data. Our threat model is that the storage server might be compromised by an attacker. And in a naively designed system, the storage server is a central point of trust. So this adversary can see the files and the data, who's accessing those files, and also serve old or modified data to users who request the data. So one strategy that's gaining increasing adoption in industry and has been explored in academia is end-to-end encryption. So the way an end-to-end encrypted data sharing system would work is that each file's contents are encrypted, and each user has the keys to decrypt the files that they have access to. Now, this works in the sense that it hides the file contents from the adversary at the storage server, but unfortunately, the adversary can still obtain a certain amount of metadata. So in particular, the adversary can look at the ACL of each file and see who has access to it, in this case, Alice and the doctor. Similarly, when Alice and the doctor actually make accesses to the file, the adversary can see that those particular users are making the accesses. So in this case, the adversary can see that Alice and an oncologist are sharing access to a file, so the adversary might be able to conclude that Alice has cancer, which is something we don't want the adversary to be able to know. So this is an end-to-end encrypted data sharing system. In contrast, Ghostor, which is a system I'm going to present in this talk, achieves two security guarantees, anonymity and verifiable linearizability. Anonymity is a privacy guarantee that I'll explain first. So recall that this is what is leaked in an end-to-end encrypted data sharing system. In contrast, Ghostor's anonymity hides this information. So in Ghostor's anonymity, the adversary can't just read the ACL to see who has access to the file. And furthermore, when the users actually make accesses to the file, the adversary can't tell that those particular users are making the accesses. So overall, the users are basically indistinguishable from each other from the perspective of the adversary. So it's basically like anonymous ghosts who are making accesses to the file, which is why we call our system Ghostor. One thing I do want to point out is that Ghostor does not hide which particular file was accessed. So in this example, the adversary will still see that file B was the particular file that was accessed by these requests. If you'd like to hide that as well, in our paper, we present a theoretical scheme called Ghostor MH that uses Ghostor's techniques and combines them with oblivious RAM to additionally hide access patterns. But the focus of this talk is going to be on the practical Ghostor system, which does not hide access patterns. So that's anonymity. Now I'm going to talk about verifiable linearizability, which is the integrity guarantee that our system provides. So you can imagine that Alice may choose to update her medical record with new information, in which case in an end-to-end encrypted system, she would encrypt her new data, sign it, send it to the storage server. But what the adversary might do is when the doctor requests this file, the adversary might choose to give the old information before Alice's update. And note that simply encrypting and signing the file doesn't help anything here because the old data is still signed by an authorized user. What Ghostor's verifiable linearizability guarantees is that if a user receives anything other than the latest write in response to their read request, they'll be able to detect it. So in this case, the doctor would be aware that an attack has occurred. So there isn't much prior work that achieves strong privacy and integrity guarantees like Ghostor. And if you look at the works that do, they typically rely on central trust in some way. So some examples of this is that they split the server into two components and assume that the two components don't collude or that only one of them is compromised. Or they might assume that the adversary is semi-honest in the case of anonymity. In contrast, Ghostor achieves anonymity and verifiable linearizability based only on decentralized trust. And what that means is that we have to architect our system to avoid having a few central machines where the trust is placed. So one example of a system like that is a blockchain. Right? So in a blockchain, there aren't a few central servers an attacker can compromise in order to hijack the entire system. Right? If an adversary wants to take control of a blockchain, they have to compromise a significant amount of the world's computing power, and that's an example of decentralized trust. Some transparency logs and peer-to-peer systems have similar properties. So the challenge that we are addressing here is figuring out how to bootstrap systems like these to achieve a storage system that's based only on decentralized trust. Okay, so one strawman approach to doing this is to just use the blockchain directly. So here's a sketch of how such a system might look like. So you have the user's machine, you have a client running on that machine, you have a blockchain. And the client would just store the files directly on the blockchain. So read, write, and create file operations would be transactions on the blockchain. And that technically works as a system based on decentralized trust. But unfortunately, the blockchain is really expensive, right? So individual operations on a blockchain have high latency, and the blockchain as a whole has limited aggregate throughput. So this system, unfortunately, would not scale very well. Instead, Ghostor system architecture still has the blockchain and the client because it's going to use the blockchain to achieve decentralized trust, but we're going to architect the system in order to use the blockchain in a minimal way. We're going to use it rarely and outside of the critical path so as to not get the expensive properties of the blockchain as well. So we have a storage server which, as I mentioned earlier, might be compromised by an adversary. And the read, write, and create file operations go to the storage server. Okay, and in order to achieve verifiable linearizability later on, the client is going to locally keep track of a summary of the operations that they are performing. Okay, so where does the blockchain actually come into the system? Well, Ghostor divides time into intervals called epochs. And at the end of each epoch, the storage server is going to place a checkpoint on the blockchain. I want to emphasize that this is one checkpoint for the entire system once per epoch, regardless of how many users or how many files or how many operations they perform. So this is just one checkpoint. And the checkpoint is small. You should think about it as being a single hash that commits the server to a particular history of operations that it performed during that epoch. OK, so once you have the checkpoint on the blockchain, then at the end of the epoch, the Ghostor client can download the checkpoint from the blockchain. It can download from the storage server the history of operations performed on the object during that epoch. And then to get verifiable linearizability at the end of the epoch, it is going to check that the checkpoint, the summary of operations, and the history of operations on the objects are mutually consistent. OK, so that's the overall system architecture. Now I'm going to talk about exactly how we achieve Ghostor's verifiable history and verifiable linearizability. And I'm going to begin with a strawman that isn't anonymous. We'll see later on in the talk how to achieve anonymity. So what we do in Ghostor is that we store on the server the history of operations on each object as a hash chain, where each node in the hash chain is a particular structure that we call a digest. So these are different parties in the system in this example. So say you have two clients, the server and the blockchain. So the first operation on each object in Ghostor is always a chmod operation that basically sets its ACL. It specifies who has permission on this object. And this is represented by a digest in green. The digest is signed by the user who issued the operation and also by the server. And then the client also keeps a local copy of it that it'll use later on for the verification procedure at the end of the epoch. Then if the doctor, say, performs a read operation, this will be represented as an additional digest. And crucially, it contains the hash of the previous digest inside of it. So these two digests are linked in a hash chain. And as before, it's signed by the user and by the server. And the user keeps a copy of the digest as well. And later operations on the file, say a write by Alice and a read by the doctor, are processed similarly. So now I'm going to talk about how the checkpointing works. And what happens is that the server is going to commit to this particular history of operations on the object at the end of each epoch. So if the first epoch ends here, then what gets placed on the blockchain is a hash of this latest write digest. And because each digest contains the hash of the previous digest and so on, this single checkpoint on the blockchain commits the server to this particular ordering of operations. So then to perform the verification at the end of the epoch, Alice will download the checkpoint. She'll ask the server for the history of operations, and she can check that the hash on the blockchain actually matches the operation, so the server can't lie about the history of operations. And then Alice can check that the operations that she performed are actually included in that history. OK, so this works for verifiable linearizability, but we still haven't answered how to make this data structure anonymous. So to do this, we observe that signing keys are like capabilities, in the sense that if I have a signing key, then I can produce a signature that can be verified by the corresponding public key. So our idea is to have different users share the same capability so that the server cannot distinguish users on the basis of which signing key they use. So concretely, each object has three capabilities, or three signing keys. A permission signing key that conveys the ability to set the permissions on an object, a reader signing key which conveys the ability to read an object, and a writer signing key which conveys the ability to write to the object. For the purposes of this talk, we can consider the permission signing key to be stored by the object's owner, which simplifies things for us a little bit. In the paper, we discuss how you can get around that storage overhead. And so now the problem gets simplified to sharing the reader signing key and writer signing key with the users who have access. So what we do is that we put the reader signing key and writer signing key into the object header, encrypted under the public key of each user who has access. So if Alice has access, she would have a part of the header that contains these two keys, and so on for additional users who might only have partial access, say only read access to the object. So this design works well so far, except that public key encryption in general hides the message being encrypted, but not necessarily the public key used to encrypt the message. So to get around that, we use a special kind of encryption here called key private encryption that additionally hides which key was used to encrypt the message. We call this structure anonymously distributed shared capabilities, because Alice and the doctor both share the same capability. For example, they use the same RSK when they both read the object, yet we aren't revealing to the server who has what permissions. OK, so going back to our verifiable history, how can we make it anonymous? Well, what we do is that instead of having each user sign their digests, we use these per object capabilities to sign the objects. And now the server can't just look at the digest, see who signed it to tell who performed the operation. So the data structure is basically anonymous. The server can no longer tell which user performed each operation. OK, so now we have a verifiable anonymous history. But one additional challenge is that a hash chain-based structure is not amenable to concurrent operations, as I'll now explain. So suppose you have one operation on the object, say is a chmod operation. And then suppose that Alice and the doctor now try to read the object concurrently. So they'll both form a local digest before they send it over to the server. And because they're both doing this concurrently, they might see the same latest digest at the server, meaning that they'll both use the same value of hash previous. OK, so they both sign this digest. They send it to the server. And now, if the server incorporates one of these two digests, it can no longer incorporate the other one because the hash previous value is wrong. Right? These three digests no longer form a chain, so they can't all be incorporated into the digest chain at the server. So to get around this, our insight is to have the client sign only over some of the fields in the digest. So if this was our digest format previously, our new digest format looks something like this, where there are some fields, like say a random nonce and the read operation itself, that are signed over by the client, and then the server is going to add on the additional fields and sign over the result. So that fixes our problem as follows. So now when Alice and the doctor perform the operation, they both form their local client digest, but it doesn't contain hash of previous. This gets sent over to the server, and then the server fills in the additional values, signs the result, and then sends them back to the client so they can use the result for verification. So now the server was able to incorporate both operations, so we're able to handle reads concurrently. Unfortunately, there's a subtle issue for writes in that there's a subtle attack the attacker can perform, which means that this technique doesn't work, which I'll now explain. So suppose we try to do the same thing. So Alice prepares her local client write digest. She sends this over to the server. And what the server can do, because the server, remember, is compromised by a malicious adversary, the server can just hang on to this and choose not to incorporate it right away. And the server can delay this arbitrarily for minutes or hours or even longer than that. And meanwhile, other operations might happen. And then at a time when it's damaging to do so, the attacker can then incorporate this digest, set the contents of the file to Alice's old write taken out of context in order to affect the final value of the file. So we call this a time stretch attack, and we need to find a concurrent write protocol that isn't vulnerable to this. So our strategy is to use a two-phased write protocol, as I'll now explain. So when Alice wants to write the file, she'll first add a prepare digest to the digest chain. And this prepare digest, as before, she'll have a local copy of it. And this prepare digest doesn't actually write the file. It just conveys Alice's intention to write to the file. And then in between the two phases, some additional operations could happen concurrently, for example, a read by the doctor. And then Alice will complete the write later on with a commit digest, where in the client portion of the commit digest, Alice signs over the hash of the server-signed prepare digest. So what's going on here? Well, if the adversary tries to perform a time stretch attack on the prepare digest, then Alice can tell that the adversary is waiting for an inordinate amount of time and can just choose not to commit. Similarly, if the adversary tries to perform a time stretch attack on the commit digest, then that won't matter either, because if concurrent write happens, Ghostor breaks the tie based on the ordering of prepare digests. So it won't actually change the final value of the file. OK, so this is the overall Ghostor stack, and we have talked about 3 of the components of it. There are a few more techniques as well. There are a few techniques around anonymous payments to make sure that clients don't abuse resources, how to hide network information from the adversary, and a theoretical Ghostor MH scheme that hides access patterns that I mentioned briefly earlier on in the talk. These are described in more detail in our paper. OK, so we implemented Ghostor as a prototype in the Go programming language. And we built it on top of Ceph-Rados, which provides a linearizable distributed fault-tolerant object store. And we benchmarked our implementation on Amazon EC2 in a multi-node, multi-SSD setup. This is a server-side latency to write a 1 megabyte object. So the yellow bar all the way to the right of the screen is the Ghostor system, and the blue bar all the way on the left is an insecure baseline. And the 4 systems in the middle are Ghostor with only some of the techniques enabled to achieve these intermediate security guarantees. So for example, the anonymity bar is Ghostor with only the techniques for anonymity, like the anonymously distributed shared capabilities, without any of the techniques for the hash chain and so on. So what we can see here is that anonymity has a pretty small overhead to achieve on top of the prior notion of end-to-end encryption. Verifiable linearizability has a low overhead on top of the prior notion of fork consistency. And overall, Ghostor achieves about a 25 millisecond overhead compared to an insecure baseline. So that's a server-side latency. So in order to get those measurements, we set certain parameters on the client to a minimum in order to focus on the processing overhead at the server. But if you look at the total latency, what happens is that Ghostor clients use the Tor anonymity network to make sure that the network information is hidden from the server. And they also employ other techniques like proof of work, which I didn't get to mention. But with these techniques, the overall latency from the client perspective is several seconds, even though the processing time on the server is only a few milliseconds. So in conclusion, Ghostor is a cryptographic data sharing system based on decentralized trust that achieves anonymity and verifiable linearizability. On a final note, I'd like to point out that given the increasing adoption of end-to-end encryption in commercial systems, we hope that some of Ghostor's techniques might be applicable to some of these systems in order to significantly boost their security guarantees. So thank you for listening, and I'm happy to take any questions now.
So correct me if I'm wrong, but the attack you described in the beginning, that a server delays the write, could kind of still happen eventually. It cannot change the order of writes, but it can still delay the write to some extent until someone noticed, right?
So you're referring to the time stretch attack?
Yeah.
Yeah, so even with the two-phase protocol, mitigating the time stretch attack depends on the client, for example, noticing that the adversary is delaying it for a huge amount of time and choosing not to commit. If the adversary, for example, delays it by a small amount, typically that isn't going to be a huge issue because concurrent writes don't have a defined order anyway in our system.
No, it's not about the ordering, it's about the delaying. You started with an example that doctor can't see the update for the allergy information or something like that.
Yeah, so for example, if Alice updates her file and the doctor, for example, a few milliseconds later then requests the file, then maybe the adversary might be able to get away with delaying that write.
Yeah.
But we're more worried about larger timescales because with the single round trip write protocol, right? The adversary is like, it isn't just a few milliseconds. The adversary could delay it for minutes or hours or a really long amount of time. And that's the attack that we were trying to mitigate.
Yeah, that's a nice problem. Thank you.
I have one question. So I know you described the talk and everything was absolutely clear for a single storage server case. Is it obvious to have distributed storage and everything generalizes?
So that's an excellent question. The way that we were thinking about achieving distributed storage is that you would kind of partition your files among multiple storage servers. So the advantage of doing it that way is that you can avoid running a protocol like Paxos in the common case. And furthermore, the overhead of maintaining a hash chain doesn't require coordination among the servers. So that would be the natural path to scaling this.
Perfect. Thank the speaker once again.